So what is the pH of a solution made by mixing 1 liter of something and whatever? So we have 4 total liters, right? All right. So how many moles of this is there? 0.12 moles of H plus, correct? How many moles of NaF? 0.15 moles of F minus. I don't care about the Cl and I don't care about the Na because neither one of them is going to grab an H or an OH and affect the pH. 0.015. Well, 3 times 0.05, isn't that? I think. Okay. All right. So in this solution, what do I really have then? I have 0.12 moles of HF, which tell your partner, is that a weak or a strong acid? It's a weak one. It is weak. And I have what left? So I have a weak acid and I have the conjugate base of that weak acid. So do I have a buffer? I absolutely have a buffer. So if I have a buffer, then I need to use Henderson Hasselback equation, correct? And it says that the pH is equal to the negative log of the Ka. So which one of these 3 do I use? All right, of HF. Plus the log, which one's on top, the B or the A or the A or the B? The B. So 0.03 and 0.12, and you end up with some number. 3 point something, is that what I saw?
I used the wrong K.
That's okay. I wasn't looking at the right one anyway. 2.5? All right, what am I doing? 2.58. That's the pH. Okay. That's not that awful. Let me look at something here. Okay, what I want to warn you, because on the test, there'll be one like this. On the test, there will be one like this. What's the difference by making that a 1?
A lot less.
All right, so I'd have 0.12 of H plus, right? And I'd have 0.05 F minus. So it's not a buffer. Now, Aisley says, so you'd use X squared. She's wrong. All right, if there's excess H plus, you just use negative log of that concentration. If you only had weak acid, that's when. And that would be if your H plus and your F minus were the same number. And that is an option I could give you as well. If your amount of H plus and the amount of anion is equal, then you don't have a buffer. You don't have excess H plus, you just have a concentration of weak acid. Okay, so we would have had 0.12 H plus, 0.05. So we would have had 0.05 moles of HF, right? But we would have had 0.07, correct? All right, and then we would have needed to take this divided by 4 and plug it in and you're ready to roll. You okay with that? Okay. Because, well, I guess I changed this to a 1, didn't I? I'm sorry. So we would have divided it by 2, the total volume.
Okay.
Sorry, that was my fault. And hey, on the Henderson Hasselback, did anyone notice I didn't divide the top by 4 or the bottom by 4 when we had these numbers? They would have canceled out. Okay, because we do need concentration, not moles, but it will cancel out in this every time because we never like square or quadruple or sorry, cube, whatever. Okay, let's look at number 2. Well, okay, one more time before we move on. Be ready for one of these where you have both acid and conjugate base. And that's your buffer, right? We're ready for that. Okay. Be ready for only excess H plus. And that is not a buffer, right? And to find pH, negative log of H plus, and it has to be concentration. Yep, so make sure your moles are divided by your total volume. Okay, be ready for only weak acid. And then that is, yep, x squared over initial equals Ka, and you take the negative log of x will be your pH after you solve for x. You got to be ready for all of those.
And the x squared divided by I, that's in chapter.
That's chapter 15, and we've done it in chapter 16 a lot. You just take the initial. So you would do this math, and let's say it was 0.12 and 0.12. So that would have made 0.12 weak acid. That would have been I. Ka is in the table. And then just solve it. Okay. Without going crazy here, if you look at that table and tell your partner, something in there is completely useless, will you tell your partner what it is? Okay, anyone know what it is? Someone said it. What? It's the Ka for HCl. First off, it's way wrong, but you would never use it anyway. We would never use the Ka for a strong acid in any of our math. It is only there to lead you possibly astray when you do that problem. Because if I only give you like, oh, hey, the Ka of this is that, well, then you're like, oh, that's the weak acid. Okay, so don't fall for that crap. Because kids, and I don't know, you guys seem to be getting this better than a lot of years. They see this and they instantly are like, oh, I got it. This is easy. Ka equals x squared over initial. Okay, so be really careful. We'll never use that one. I'm giving you too much. I said too much. All right, here we go. Number 2, a buffer. That makes this problem way easier. Contains holy sig figs. Oh, what a pain. So how many digits should your number have in it? 4. All right. And if on the AP test, if you just put like 0.28, you would get 1/2 of the credit for this point. Moles or whatever. It probably asks for pH, but whatever. Like this, you better give me 4. All right, a buffer contains that much formic acid and that many moles of sodium formate in a 1 liter of solution. Calculate the pH. We can do this all day long. I have this right here, right? You okay with that? If you're like, well, I don't know the Ka. Well, it was up on there. So pH, negative log 1.602 times 10 to the negative 4 plus log of B, which is which one? Tell your partner. All right, the one from the salt. So that's 0.6, right? I don't know why the decimal's there, but it is now. And 0.4. And something wrong, Delaney? What? 0.2. Why? Okay, this is a really good point. And you fell for a trap, and it's a very well hidden trap. She did the science. She said, wait, I would make that much weak acid and have the difference. You don't do that. Now, why? You get it probably, but everyone, oh, you don't? Okay, it's because it already gave you the amount of acid. So this is the exact amount of acid that I've put in. It's not going to react with its own conjugate base to make more acid because there's no more H plus in there. So yeah, so if it, now this will sound tricky, but if it says a buffer solution, don't do chemistry, only do math. And if it doesn't say, nowhere in here does it say buffer. So I have to first do chemistry and then do math. Okay, because everyone falls for this. I forgot to warn you. When they're especially back to back, you're like, okay, I got it. I just did this. I find the difference. That's that. Nope. If it's a buffer, it gives you both the values. Like if it says it's a buffer, it gives them to you. Okay, lots of traps around these. Like this equation right here, we can do it all day long, but it's chemistry first sometimes, and then that's the hard part. Okay, anyone have that answer typed in? 3.97?
3.972. We only need 4. I know.
Well,
That's what
four
we're
after.
3.972.
4 total. 4 total. If we were adding, yes.
Okay.
Multiplying, we just take the total. Listen,
The next digit is a 9. I don't know what that digit is. It's a 4. Oh, just because I didn't add the 0.02 at the end of it. Yeah.
well, yeah, that's because, okay, shh, let's not pick on him, because guess what? The AP test believes in second chances. You could get this right if it was a 1 or a 2. They give you plus or minus 1 on that value. That's it. So they're super kind. They give you 1/1000th off. Like, oh, I guess I'll give it to him because he didn't put in the 0.02. All right. Okay, this is a great question, and AP asks these style of questions all the time. If 100 milliliters of this buffer is diluted to a volume of 1 liter with pure water, the pH doesn't change, which seems super crazy. Why won't why discuss why the pH remains constant on dilution? No, that's the trap. Again, that seems like, oh, easy, it's a buffer. This has nothing to do with it being a buffer. I know. Davis. No.
Because the ratio of the acid to base doesn't change at all.
Sort of. You're missing a key word that's huge. What? Okay, that's true, but not the answer. We're missing a big word. Is it Zeph? What the hell? I don't know. Zeph. No. My bad. My bad.
Okay.
I don't know where that came from. I apologize. No. Oh crap. At least it's glittery. Like, look at that. What are we studying? 3 chapters. Equilibrium. Listen, the system, if we add more water, more of it dissociates to maintain what word? Equilibrium. And it will maintain the same concentration until we run out of one or the other. You with me? The word is equilibrium. The concentration would remain constant because it's going to maintain equilibrium the entire time. I'm going to have glitter on me for 10 years now. Good point. I might. All right. Feel good about that. Do you feel good about that? Okay. I thought me putting an E would make it super easy.
It's like one of those like just goes up your head.
See, a lot of energy.
Okay, here we go.
Raise it because somebody will get confused when they watch the video.
Wow.
That'll make it much better.
Equilibrium. Okay, letter C. You can do, no, equilibrium, the way I write is easier than Zeph. You can do letter C on your own. I'm going to pause it while you try so I can go to the bathroom, actually. And then we said a lot of stuff that I didn't record, and we got this. Merry Christmas. Okay. All right, so we're just doing these 3 practice problems. These KAs are just, they may or may not be helpful. All right. I'm doing it. Okay. So first things first is number 1, a buffer. No, it's missing the 2 requirements. You have to have both a weak acid, or I got to be careful, or a weak base, and their conjugates. Okay, I in the book's the same way. We teach everything acid, and then we're like, yeah, and it works for bases too. Well, this is a base problem, right? So ultimately, at some point in time, I'm going to take 14, and I'm going to subtract anything I do here. Are you okay with that? I'm going to start that way so I don't screw up. Okay, now you may not have known that by just reading it yet, but this is how you would understand, or sorry, you would figure that out. 1 times 0.1 means 0.1 mole of H plus, right? All right, 2 times 0.06 means 0.12 mole OH minus. I guess you should be able to read this, by the way, immediately and know it's not going to be a buffer because it was a strong base and a strong acid. So this is a neutralization reaction, not a buffered reaction. So we end up with which one being in excess? All right, excess OH minus, and it is 0.02 moles. But I must do what to this? Not yet. Divide it by 3. So I'm going to just say the negative log of 0.02 divided by 3. All right, and that equals 2.17, which all the way over here, I warned myself I had to subtract whatever this answer was from 14, and that ends up to be all right. Okay. You got to know that I typed this one and I'm pretty lazy. The answer would have been 12 technically, or 11.83. I don't care. If I type it, I'm not too worried about it, but we should definitely start practicing answering with sig things. So it would have been 12. You okay with the process? If you see strong acid, strong base, find the excess H plus or OH minus, negative log it. If it's H plus, you're golden. If it's OH, subtract that answer from 14. I do not know. I'm going lefty. Are we ready? All right. So, oh, have we even done number 2? Raise your hands if we did it. If I have a critical mass. Okay, that's good. 2.15 times 10 to the negative 6. All right. Do you need more time on number 2? Or are you still working on 3? What, Seth? Seth, excellent job on junior prom. I really appreciated how you moisturized the floor as the day or the dance went on. That was good weather. Like that was a weather phenomenon. It got so hot and humid.
Inside of the building.
We did that. The cement, it condensated onto, we met the dew point,
That is so disgusting.
but that's what we did.
Why are you proud of this?
It's kind of cool
Cool.
to make your own weather in a building.
Yeah, but it's gross.
It's gross, but it's cool. We made it hot enough that our own moisture condensated on the cement.
It was cool. Actually, it was hot.
Yeah, that's really fun to think about.
Okay.
It was so gross.
That Farmington kid took his shirt off and used it as a towel, and it was soaking wet. Like it would drip.
Thing is, that was probably my day.
Well, I wanted to throw him out, but
Yeah,
We should
the
have
poor Farmington boys were.
they got a lot better after they were buttholes, and I went and took a picture of all of them right to their face.
You scared them by doing that.
That was my point. And they were way better after
And
that.
I went in and they're like, that dude just came up and took a picture of us. Are we in trouble?
Oh,
Yeah, it's Davidson.
it's a good guess. Okay, here we go. Number 2. Is this a buffer? I haven't done the math myself. Is it a buffer? I have a no and I have a lot of yeses. So we'll say it's a yes. Okay. So it gave me a strong acid and it gave me a salt. So if I have strong acid and a salt, I got to do chemistry first. So I have 0.11 of H plus, right? Is this 0.24? So I end up having 0.11 HF and 0.13 F minus. All day, every day. Henderson Hasselback that thing, right? And what did we end up with? Raise your hands if you got that one right. Okay, hopefully easy. Okay, nitric acid. That was rude of me. I didn't give you the formula. Yep, I almost put H3NO. Okay, do we have it done or you need a minute to do this one? Okay, I'll give you 2 more minutes. Someone make sure I unpause. Is this going to be a buffer? I think the answer is no, but it looks like it might be. We have strong acid and we have the salt of a weak acid, right? So we just have to do the math. We have to do chemistry, sorry, and then math. So we have 0.2 mole of H plus from here. Because this is strong, so it completely dissociated. Oh, hey, I love when math is cool. I have 2 of 0.1, which means 0.2 mole of CN minus. These will combine to make the smaller of the 2 values of weak acid. So I make 0.2 moles HCN. And then the difference between them would be the amount of salt, and that is what number? 0. So there is no buffer here because it's missing the conjugate base that would grab the H if we added acid. Okay, it has the part that can neutralize the base. It's just missing the part that can neutralize the acid. So it's not a buffer. So this is a weak acid, correct? All right, so to find the pH of the weak acid, I have to solve for X and take the negative log of X, right? So the Ka, 2.15 times 10 to the negative 6, Ka equals X squared over the initial, which is the thing that was formed. I guess I should circle that part. Yeah. So I multiply this by 0.2, take the square root of it, and take the negative log of all of this. And what do I get? 3.2. Thumbs up. Okay. I feel all right about it. I don't know. I need to check with you guys. Oh, look at that. This must have been a combined chapter. Oh, shoot. Oh, I still got more to teach. A lot more than I thought. I forgot. We have KSP coming up. Don't complain. KSP is the easiest of all of them. Go ahead. Good stretch. My fault. I shouldn't have even looked at you. I know, Mr. Perfect. Okay, we are going to change what we're talking about in a slight way. We're going to move to something called a titration, which we did already learn, if it sounds like a word you've heard before. We're just going to go a little bit more in depth. Now, a titration and buffers, nothing to do with each other. Yep. It's just neutralizing something. All right. So, I mean, we're not there yet. This doesn't say titration, but we're getting there quick. So the pH range, this is not like the most important part ever of the buffer. But the pH range is the range of pH values over which a buffer system works effectively. So like your blood, we need to keep it right around, I don't know, 7.2 or something. What is it? 7.4. All right, so we need a buffer that is very good at maintaining that, which is the carbonate bicarbonate buffer system. We wouldn't want something that only has a range of like 3.5 to 4.5. That would be completely useless. So it's best to choose an acid with a pKa close to the desired pH. All right, the range of buffer is generally within plus or minus 1 of the pKa. So what that means is we are given this acid right here. You take the negative log, 7.1 times 10 to the negative 4, and someone tell me what that is. .15. So the pH range of this buffer then, we would say, is between 4.15 and 2.15. This buffer, and it doesn't say what acid it is, but it would give you a name of the acid. This would be good if we needed a system to remain around 3.5 to 2.5. Okay, we wouldn't pick an acid conjugate base pair that was outside of this range. The only time, let's see if it's on this next slide. Nope. The only time this is really asked is it will give you, it's in the multiple choice, and it says which acid base pair below would be the best buffer system to use to maintain a 2.8 pH or something. So you just literally take the negative log of all the Kas, and the closest one to 2.8 is the one you take. There is a question like that on my exam, if I remember right. Okay, so you just take the negative logs, and the answer is the one that's closest to it. Okay. Next, this is, we won't do this problem right now. This is the same exact thing, but it's from a solid, which we did a little while ago. If it's not just two liquids, we can still do it. You just have to divide this by the molar mass. Like we can do it. We've done 2 of them this way. Okay, titration is a whole new thing that I have 4 minutes to teach. So we'll spend all day tomorrow on titration. So we'll call it good. Yep. Oh, you said thank you? Yeah. Oh, you're welcome.